Welcome to the Are You GCSE Physics Ready playlist. This playlist is packed with example questions and guided solutions for every GCSE Physics topic. So it's the perfect tool to help you test your understanding. If you feel like you might need a quick review of this topic before having a go at the questions, or you would just like the ideal revision companion for these videos, then do make sure to download my free GCSE Physics revision notes, linked in the description below. If you're ready, let's dive in. Okay, let's look at some questions with our momentum equation. So our first question on the left is, what is the momentum of a car on a motorway? And we are supposed to estimate it. So as always, let's write down the formula we're using first. P, that's what I'm using to be momentum, represent momentum, is mass times velocity. Okay, so now I need to think about what is roughly the mass of a car and what is roughly the speed a car is travelling at on a motorway. So I'm going to guess the mass of a car could be roughly 1,000 kilograms and the speed of a car would be roughly 25 meters per second. So multiply those together, 25,000, and yes, my units for momentum are as simple as kilogram meters per second, multiplying my mass and my speed. Okay, next example. What is the momentum of a 50-gram bar of chocolate flying through the air at 5 meters per second? Well, I'm using the same equation here, and the only thing I need to be careful of is in my equation, my mass, as always, should be in kilograms. So first, I need to convert that 50 into kilograms by dividing by 1,000, 0.05, multiplied by 5, the velocity, and that gives me 0.25 kilogram meters per second. Okay, now we're going to look at some collision style examples. So we've got a car moving 15 meters per second with a mass of 2,000 kilograms, colliding with a stationary car with a mass of 1,000 kilograms, and the first car then moves off with a velocity of 5 meters per second. What is the velocity of the other car? So first and foremost thing to remember when we're dealing with collisions and momentum calculations, my momentum before is equal to my momentum after, and I would always recommend writing that statement in your exam first. Next, there's a lot of information in that question. It took me ages to read it out, so I'm going to draw a little picture of what's going on so I can see things more clearly. Okay, so I've labelled one car A, one car B, and I've put all the relevant masses and velocities next to them for both the picture before and the picture after. Okay, and then this is how I tend to structure my answer to this. I'd start with all of the befores, that is, calculating all of the momentums of the two cars before. So I'm going to start with car A, its mass 2,000 times its velocity 15 gives me 30,000, and then I need to calculate the momentum of car B, and that is its mass 1,000 but it's stationary, so multiply by 0 gives me 0. Good. So then I can find what is the total momentum before by simply adding those two together, and so that is 30,000 kilogram meters per second. Good, now I turn my attention to the momentum after picture. So I'm going to start with my A again, and that's mass is 2,000 kilograms times 5, that's where that 10,000 has come from. And then for part B, this is the one where we don't know what the velocity of the car is. So I've got the mass 1,000 times some velocity that I'm calling V for the minute. Okay, so that is 1,000 V. Right, now I need to refer back to my original statement. Momentum before is momentum after. My momentum before in total was 30,000. My momentum after in total is this 10,000 plus this 1,000 V. Now I've got an equation, all I need to do is rearrange it to get the right answer. So first, I'm going to minus that 10,000 from both sides, so that gives me 20,000 is 1,000 times V, and then if I divide through by that 1,000, that's my next line where I get 20 meters per second is my velocity V. Always good to then sense check. The velocities I've been using in these questions are roughly 50 meters per second, 5 meters per second, so 20 sounds like a sensible order for that velocity.
Okay, another star question. Car moving at 15 meters per second with a mass 2000 collides with car traveling in opposite direction at 10 meters per second, mass of 1000. A 1,000-kilogram car moves off in the opposite direction to what it was traveling in at 30 meters per second. What is the velocity of the other car? Okay, so again, let me write my statement first that I'm dealing with. Momentum before equals momentum after. And then I'm going to draw the picture again to simplify all of those words and numbers in that question. So we have a picture that looks like this. Now, having a look at the momentum before picture, and for A, we've just got that 2015 meters per second, and it was kind of traveling off one direction. And clearly for this example here, I have picked going towards the right as being positive. Okay, because it then told me that car B moves in the opposite direction at 10 meters per second, which is where that little minus sign has come from, because remember, velocity is a vector. Okay, so if I set everything towards the right as positive, that means anything towards the left has to be negative. Okay, and then the momentums after. The A one is the one that I'm not sure, but it tells me that it rebounds in the opposite direction. And the B one, okay, that's now 30 meters per second, and that is positive because it told me that it ends up then going off towards the right. Good, so again, I'm going to start with the momentums before. So for A, that's 2,000 times 15, 30,000. And for B, mass 1,000 times velocity minus 10 is minus 10,000. So keep the minus signs in there because now my total is 30,000 plus minus 10,000, which gives me 20,000. Okay, now let's look at the momentum after. So for A, I've got 2,000 times some velocity v, not sure what that is yet, and B is 1,000 times 30 is 30,000. Okay, so next thing I am going to do is write the total there for my after equation, which is 2,000v plus 30,000, so that I can set my total before 20,000 equal to that total after. Now it's time to rearrange this equation, so bring the 30,000 over to the left-hand side by minusing it, so that gives me minus 10,000 is 2,000v. And then dividing minus 10,000 by 2,000 gives me minus 5 meters per second. That's good. I'm glad it is a minus because A travels off to the left after this collision. Okay, so that should come up with a minus sign, so that's all good. Okay, this time we have a toy car of mass 500 grams moving at 2 meters per second, slamming into a stationary toy truck of mass 1.5 kilograms, sticking together, and what velocity do they move off with? So getting bored of this by now, but momentum before equals momentum after, and then drawing my little picture of what's going on here. Okay, so A and B, and then AB together. So that's why I've got 2 kilograms in my momentum after, because they actually become 1 unit. Okay, so the total mass of that new object is now 2 kilograms, and I'm looking for that velocity they move off with, v. So let's look at before. 0.5 times 2. So 500 grams. Remember, my mass needs to be in kilograms in this equation. So 500 grams divided by 1,000, so where that 0.5's come from, times 2 is 1, and the momentum of B is 0. So in total, I have a momentum of 1. Then in my after picture, I have A and B together, and they are moving at mass 2 multiplied by velocity v. So their total momentum is 2v. Okay, setting momentum before 1 equals momentum after 2v. Gives me, if I divide through, that v is 0.5 meters per second. Okay, final one of this type, and this is just sort of taking you through each different type of example. 2 ice skaters pushing away from each other, one of mass 60 moves at 2 meters per second. What speed does the other skater with a mass 80 move off at? So momentum before equals momentum after, and a picture. So before, they're both together, they're both moving at 0 meters per second, and then afterwards they push away from each other. Okay, and again, because I've got that 2 meters per second there for part B, I've clearly chosen to the right to be my positive side. Picture before, not very interesting. Because these are both stationary, 80 times 0 plus 60 times 0 is just 0. So then my picture after, I have got 80 times some velocity v that I need to work out. And for B, 60 mass times 2 is 120. So in total after, I've got 120 plus 80 V. Setting before equal to after means setting 100 equal to 120 plus 80 V. Then moving my 80 V over to the left-hand side of the equation, so minusing it. I've got minus 80 V is 120, and then I divide through. 120 divided by minus 80 is minus 1.5. Again, happy with the negative sign because it's travelling towards the left, which I set as negative. Okay, now we're going to use that force equation that we had to do with momentum. And firstly, I've just copied the question across from the other slide, but we are going to use that information in that scenario to do the following bit. The explosion lasts 5 seconds. What is the force on both skaters? Okay, so in order to do this, I need to write down some information that I had for the two skaters. So skater A, I know that they started at rest. I know that they finished at minus 1.5 meters per second because that's what I calculated. And I know that their mass was 80 kilograms from the question. Okay, and then same for skater B. Their initial speed U is 0. Final speed V was 2 and their mass was 60. Good, so what is the equation that I'm using? I've got force is mv minus mu over t. So let me do the force on skater A first. So I'm just going to take all that information and place it in the correct part of my equation. Force on A, their mass 80 times minus 1.5 minus 80 times 0 all divided by 5 is minus 24 newtons. Okay, and that minus sign just tells me the direction that the force is acting in. Let's do the same for B. This time 60 times 2 minus 60 times 0 divided by 5 is 24. Now you might notice something about those two values, which is they have the same magnitude but they're in the opposite direction. This is because this is an example of Newton's third law. Two objects interacting, skater A and skater B, exert equal and opposite forces on each other, hence the 24 and the minus 24. Okay, so sometimes in your exam you may just have to state what the force would be on the other object, okay, and the reason you're meant to know that is because it's the same size and the opposite direction. Okay, enough maths, let's deal with some explanation style questions. So we have, explain why an egg being dropped on a carpet is less likely to smash than an egg being dropped on a wooden floor. Okay, first things first, try to avoid talking in terms of energy transfers here. It would generally overcomplicate things. When you see a question like this, which is basically asking you why the force on one object would be less than the force on another object, you need to be using that equation we've just looked at. So first things first, just write that out. Force is this. Okay, and then you need to say the following. If you had a very big T, as in a very big time, a very large denominator, that would give you a small force because you're dividing by a large number. Okay, so that would make your force smaller and smaller and smaller. So you need to state that next. Then you need to refer to what the question is asking you about. So the carpet gives you a longer time of colliding. So your egg is kind of slowing down for a longer time. I think you can imagine that when it's on the carpet than when it's on the floor. Large T, small force on egg. And then finally explain what that means about it smashing, which is less force, less damage to your egg. Okay, now some questions to Newton's third law. So explain why the forces involved in a collision are a Newton's third law pair. Well, they satisfy all of the criteria for a Newton's third law pair. That is, they are the same size, they act in opposite directions, and they act on the two opposite bodies, whichever two objects were colliding. Okay, next question. Explain whether, for a parachutist travelling at terminal velocity, the person's weight and drag are a Newton's third law pair. Well, if I show you the free body diagram of this, if the person's travelling at terminal velocity, the drag upwards would be the same size and the opposite direction to the weight downwards, okay, because there needs to be no resultant force so that this object is travelling at this constant velocity. However, no, they are not a Newton's third law pair. Why would be the question, and it's because they are acting on the same body. They are both acting on the parachutist. So you might be asking, well, okay, well, what are the Newton's third law pairs in this scenario then? Well, actually, the drag is a pair in the sense that the force that the air puts onto the body of the person exerts an equal and opposite force onto the air around them. And for the weight that the earth pulls down on the person with, the person is actually pulling upwards on the earth with the same force. Okay, you just don't see the earth moving upwards because its mass is so large, so any effect of that force is negligible.
Just before we go into the tips and tricks section, if you do want some extra advice to getting that grade 9 for your GCSE, then why not download my free 20-minute exam success guide? Just click on the link in the description below. I'm going to give away all of my best advice and secrets, and completely for free, so why not?
Okay, tips and tricks for this question. Firstly, your classic force question with the egg smashing. They can use loads of different contexts, but remember, just write down that equation, explain t being longer, and go from there. Okay, adapt it to the scenario that they've given you. Minus signs, keep them in. Momentum calculations and that force equation, it's very important that if one of your velocities is negative, that you make sure to keep the minus sign there, okay? Otherwise it could change your final answer. And finally, my tip for Newton's third law is that these forces have to act on different bodies. It's not enough for these forces to just be balanced, i.e. equal size and opposite direction. That is not a Newton's third law pair, and that is by far the most common misconception about Newton's third law pairs, okay? They must act on different bodies. But that makes all of the forces involved in momentum collisions Newton's third law pairs.